Okay, as a quick reminder, we looked at the first four passive transport mechanisms: simple diffusion, diffusion directly across the membrane using Fick's law, diffusion through channels, and looking at facilitated diffusion and the three properties that are shown with specificity, competition, and saturation. So where we left off was we're going to start osmosis. Osmosis is a special case of diffusion, and it only refers to the movement of water. In order to have that, you have to have a semi-permeable membrane, meaning water can go across, but some particles can't. So a textbook definition would be net movement of water across a semi-permeable membrane from an area of high to low water concentration. Some people like to think from an area of low to high solute concentration. And part of that is because typically we don't measure solute and water the same way. So as an example, if I said we're pure water, we have pure water, what's the solute concentration? You go, there's nothing in it but water, so the solute's zero, right? Solutes are things dissolved in water. If we have a 10% glucose solution, what do we have? Well, 10% of the particles are glucose, which means 90% of the particles are what? Still water. So the osmolarity determines osmosis, and osmolarity is just a measurement of the osmotic pressure. Right, and we saw this calculation in lab 1. Osmolarity equals the molarity. So osmolarity, which is abbreviated OSM, capital OSM, equals molarity times the number of dissociable particles. Now, when we look at osmolarity in the human body, we often describe it with tonicity. Right? And tonicity will look at things that can move across the cell membrane and bring water with it. When we look at tonicity, we have to remember two types of particles: penetrating, things that can cross the membrane, and non-penetrating, things that can't cross the cell membrane. And again, remember, water, even though it's polar, is freely movable across the cell membrane. And so when we look at tonicity, we're really talking about the concentration of non-penetrating solutes. And we'll work on some problems here eventually. So when we look at tonicity, we can describe it as hypotonic, hypertonic, or isotonic. All right, and so let's kind of start with iso, even though it's down here on the bottom. In isotonic, the actual definition says there's no change in cell volume. So here's an example of an isotonic solution, and just as much water is entering as it's leaving, and that's because the osmotic pressure inside a cell is the same as the osmotic pressure outside. Might as well learn this number now. It's 280 milliosmoles for human blood, so 280 milliosmoles, or 0.28 osmoles. So 280 milliosmoles would be isotonic. Now, if we have a solution that has less than 280 milliosmoles, then what's going to happen is cells are going to swell when we put in the solution, and that's because when we have less particles outside, smaller osmotic pressure, more particles inside, larger osmotic pressure, that's going to pull water in the cell. When it does that, the cells get larger. In some cases, if you have a big enough difference, cells get so large they lyse. That's called hemolysis. Hemo, blood, lysis, break apart. In hypertonic solutions, cells shrink. And so if there's more particles outside in terms of concentration than inside, the outside would have a higher osmotic pressure, and that would pull water outside, and the cells would shrink. All right, so again, look at the numbers. Isotonic is 280, Anything less than 280 is hypotonic. Anything more than 280 would be hypertonic. Okay, so that's kind of how you figure it out. Sometimes we don't want to look at just tonicity, but we want to look at what's called osmicity, or sometimes known as osmosicity. Now, osmicity looks at the initial conditions of the solution in the cell, while tonicity looks at what happens to cell volume when you put it into a solution. And osmicity is so easy, people mess it up. All right? So when we have more particles, let's start at the beginning again. Let's do it this way. When we have the same number of particles inside the cells outside, it's isoosmotic. When we have more particles outside the cell, it's called hyperosmotic, and less particles outside the cell, it's called hypoosmotic. Okay, that's the initial condition. And then we let molecules move, and based on what happens with the molecule's movement, then we can figure out what's called the tonicity, which we just talked about. Now, I mentioned this before. When we calculate the osmolarity, you should be able to calculate the molarity and then multiply it by the number of dissociable particles. I had mentioned that there are only 5 substances we're going to have to know, these 5, for exam purposes. So if this doesn't make sense to you about NaCl dissociate into 2 and KCl into 2 and CaCl2, calcium chloride into 3, glucose and urea 1, then memorize this and just be able to do those calculations to figure out the osmolarity. There are 5 steps to determining osmicity and tonicity. The first step is to make sure you convert everything to milliosmoles. All right, so convert to milliosmoles. You want to make sure you're in the same units. And to do that, again, you just use that formula, millimoles times the number of dissociable particles. So as an example, what happens if I said, oh, we have 140 millimoles of NaCl? All right, so I'll go back here and go, okay, NaCl, oh, look, there's 2 dissociable particles. I said I have 140 millimoles, means 140 times 2 dissociable particles. Again, NaCl, 2 dissociable particles here at the top. So that gives me a milliosmolarity of 140. All right. Human cells are 280 milliosmoles. And so unless it's stated otherwise, then we're always going to go with that magic number 280. But don't just assume, make sure you look at the problem, because we could look at some different things that wouldn't be 280. When you do that, then you just determine the osmicity. And all you do is you compare the solution to the cell. That's it. Solution to the cell. You don't do anything else yet. You just solution to the cell. If there's the same inside and outside, it's isoosmotic. And so we said, oh, when we did our initial thing of NaCl, right, sodium chloride, it was 280. So it's 280 milliosmoles inside, right? We always assume a red blood cell is that unless we say otherwise. Outside we calculate is 280, 140 times 2. So it's isoosmotic. Okay, so that'd be osmicity. Number 3 is move any impermeable substances. There are lots of substances that are permeable in the cell membrane. Okay, but if we look here, the only one of the 5 we're responsible for is urea. Glucose, calcium chloride, potassium chloride, sodium chloride cannot move across the cell membrane. So the only one that can move from one side to the other is urea. So if you have urea, you move urea. And if you don't have urea, you're done. The reason why we move urea is there are pretty much 0 urea molecules inside a red cell. So if you have a solution that has urea in it, then urea is going to diffuse into the red blood cell until it reaches equilibrium. So basically you have to split the urea, half stays outside, half diffuses in, and once half diffuses in, we reach that dynamic equilibrium, and so we can move that many particles inside. Once we have that, you draw an arrow to the biggest number to show the water movement. Okay? So the easiest way to do it is draw an arrow pointing to the biggest number. In our little experiment, right, we got 280 milliosmoles inside, 280 milliosmoles outside, so we'd have a double-headed arrow. There'd be no net movement of water. Based on what happens to the cell volume, and because of the direction of our arrow, you determine the tonicity. In our case, since the arrow would be double-headed, there'd be no movement of water in or out, net, we'd have an isotonic solution, right? The cell would not change volume. So that's kind of how you figure it out, pretty simple. So let's look at the case where we have I don't know why I have 100 here and 70 here. So change this to 100, right? So 100 millimoles of calcium chloride. You look in that table, it's 3 dissociable particles. So the milliosmoles in the solution, right? The milliosmoles in the solution would be 300, right? You determine the osmicity. More particles in the solution than the cell. So it is hyperosmotic. Move any permeable substances. In our case, it's just urea. There is no urea here, so don't worry about it. So now we draw the arrow from the smallest to the largest. Since it's 280 in the cell, 300 in the solution, I draw an arrow towards the solution. That means water is going to leave the red blood cell, right, and go into the solution. So the red blood cell is going to shrink. Red blood cells shrink in a hypertonic solution. And if you just follow those 5 steps every time, it's pretty simple. Now, we have a situation, right, where we have 70 millimoles of KCl and 140 millimoles of urea. Okay, so first of all, our first idea in terms of our example, I'm not going to do them all, but here's another, this is a good one, is we don't have the same units. We're supposed to be milliosmoles, we're in millimoles. So remember, we multiply by the number of dissociable particles. So 70 millimoles of KCl, we multiply by 2 dissociable particles, times 2 is 140. 140 millimoles of urea. Urea has a dissociable particle of 1, if you look at that table, so that's 140. So 140 of KCl, 140 of urea gives me a total osmolarity of 280. All right, so now I have my solution. My solution is at 280. Right, my red blood cell is always going to be 280. Right, so now I just go, oh, look, there's 280 particles in the solution, 280 particles in our red blood cell always. That's isoosmotic, right? So I'll come over here and go, that's isoosmotic. Now, number 3 is move permeable substances, and in that case, it's urea. All right, so remember, I'm just going to draw it down here, and again, it's hard to do with the mouse, but I'll try. So there's 280 inside the red blood cell, 280 in the solution. All right, now since urea is in the solution and urea is permeable in the red blood cell, half of the urea is going to diffuse inside the red blood cell. Okay, so 70, because there's 140 millimoles of urea, 70 millimoles of urea is going to diffuse inside the red blood cell. So since it diffuses in, I'm going to cross this number out. I'm going to say, okay, this number goes from 280, 70 moves in, it goes to 210. So the solution now is 210. Because 70 came in to the red blood cell, it goes from 280 plus the 70, that makes it 350. All right, so now inside the solution is 210 because half the urea went into their cell. Right? The red blood cells now the 280 that started there plus the 350. We don't have to move KCl because remember, that's not permeable in the cell membrane. Right? So number 4 is draw the water movement. So I just draw an arrow from the smallest to the biggest number, which in this case would be to the 350. So water is going to go and move into the cell. When water moves into the cell gets larger. Cells get larger in a hypotonic solution. So you should be able to do those problems pretty easily in terms of the cell. So this is a good example of osmicity and tonicity are not always the same. And again, this kind of shows osmicity and tonicity and what they would look like. Lab 7 and 8, we're going to put red blood cells into different solutions, at least look at them under the microscope and see what happens. And we'll look at different tonicities. And this is what red blood cells look like. So isotonic, they tend to be large biconcave discs, right? Notice how big that concavity is on most of these, right? It takes up most of the cells. Notice the cells are not always perfectly round. They actually tend to be more towards oblong. In a hypotonic solution, you can see these blown up cells, right? There's no concavity, and in fact, you see cell fragments because some of them blew up. Then in a hypertonic solution, we've sucked water out of them. You see these little spiky things because the cells have shrunk. That's hypertonic. So let's talk a little bit about active transport then. Remember, active transport, there's a couple things that you have to rely on. One is we're going from some low to some high, whether it's concentration or some other factor. We're going from low to high. And because we're going against a gradient, at some point in time, it requires some sort of energy, some sort of ATP. There are two types of active transport we're going to talk about, plus a couple other ones that come under the heading of active transport. And the first type of active transport we're going to talk about is called primary active transport. And then we'll talk about secondary active transport. Primary active transport is direct. It directly uses ATP. Right? So we take ATP and break it down and use that energy to actively move molecules against their gradient. To be honest, there's only 4 primary active transport mechanisms in the human body. That's it, 4. And for secondary active transport, it's an indirect use of ATP. You'll see what I mean by that in a second. And it's called secondary because it uses gradients that have been established by primary active transport. So they're secondary to primary. So a great example of primary active transport is what they call the sodium-potassium pump or the sodium-potassium ATPase. Okay, so it's shown right here. An ATPase is an enzyme that, not surprisingly, and you see it ends in ACE. We've talked about enzymes a little bit. They tend to end in ACE. That breaks down ATP. And when it breaks down ATP, it gives us energy. And so what happens is we take ATP here and turn it into ADP. So that's the energy we have for it. That's why it's called the ATPase or pump. And what we do is we pump molecules against their gradients. So let's kind of look here. So let's take a look at sodium first. So outside, I'll circle sodium outside. It's 145 millimoles per liter. That's its concentration. Inside, it's only 15. All right, so sodium's diffusion gradient is into the cell. But if we look at potassium, that's the K plus, right? Inside, it's 150. Outside, it's only 5. So potassium would want to diffuse outside down its gradient. And in fact, during certain cellular processes, sodium diffuses in and potassium diffuses out. But we can't let that continue without doing something, because if potassium continually went out and sodium continually went in, eventually it would reach equilibrium. And in most cases, and especially with cellular functions like this, equilibrium equals death. And so in order to maintain sodium in a high concentration outside and potassium in a high concentration inside, we use the sodium-potassium ATPase. And what we do is we pump 3 sodiums out. So notice the arrow is going out. That's against the gradient, right? Sodium's supposed to go in. That's against its gradient. And at the same time, pump 2 potassiums in. All right? This is a primary active transport mechanism because we're breaking down ATP, right? So we're breaking down ATP to ADP. And it does a couple things. First of all, it helps to keep the inside of the cell negative in terms of charge. Why? Well, think about your checking account. If you spent $3, so 3 sodiums out, for every $2 you made, 2 potassiums in, right? $2 in your checking account, $3 out, you would eventually lose all your money, right? So that helps keep the inside more negative. That's actually a good thing. We'll talk about that later on this semester, right? And because of that, it separates charge. It's called an electrogenic pump sometimes because it generates electricity, and all electricity is the movement or separation of charge. So that's the sodium-potassium pump. There's only 3 other ones. As an example, the hydrogen pump in the mitochondrial membrane for the electron transport chain is one. And calcium is another one that pumps calcium in muscle. So that's primary active transport, and that's the one you should know, the sodium-potassium pump. It's a little different figure of it, but it just shows the 3 potassiums going from low to high, lining up here, spitting them inside, and then the 2. So 3 sodiums in, and then the 2 potassiums. Actually, this is 3 sodiums out. 3 sodiums out, and then the 2 potassiums in. It's also showing the ATP, right, and breaking it down to ADP and using that to fuel this. So this is just a graphical representation of what we just saw. So we said it's an electrogenic pump because, again, it helps the inside of the cell become more negative and the outside is more positive. Talk more about this phenomenon when we get to nervous system. The other thing that the primary active transport does is it maintains what's called disequilibrium. And I'm not sure why students have a problem with disequilibrium, but let's look at this figure right here again. So if I said, all right, if a substance was in equilibrium across this membrane, what would that mean? I think most of you would say, okay, let's say, we'll just say substance X, whatever that is. You would say, oh, if it's in equilibrium, it means there's the same concentration inside as there is outside. Perfect. So if I said, if it's in disequilibrium, what does that mean? Well, it means it's not in the same concentration, right? So Na plus sodium is in disequilibrium. It's a high concentration outside, low concentration inside. Potassium is also in disequilibrium, but the opposite way. It's a high concentration inside, 150, low concentration outside, 5. So by the sodium-potassium pump, it maintains that disequilibrium. And that disequilibrium is nice because what it's going to do is it's going to allow us to move one molecule, at least, down a gradient while moving another molecule against its gradient, okay? So here's an example where we have a high concentration of sodium. And again, sodium is high concentration on the outside because of the primary active transport mechanism we just talked about, the sodium-potassium pump. And so we're going to diffuse sodium into the cell. Okay? At the same time, we're going to piggyback another molecule with it into the cell. And so in this case, this molecule, this purple one, is going against a gradient. And a great example of something that works like this is called the sodium glucose transporter. Sodium moves down its gradient into the cell, and it brings glucose in along with it. That's often against a gradient. Since it's moving against a gradient, it's an active transport mechanism. Where does the energy come from? Well, the energy comes from, this is why it's called secondary, from the already expended energy to keep the disequilibrium of sodium, i.e., keep sodium in a high concentration outside the cell. So it relies on the disequilibrium generated by primary active transport. That's called the sodium glucose transporter. All right? And again, we saw these terms before. You can move a molecule in and a molecule in at the same time. That's called co-transport, or called symport. We can move one in and one out, right? Or multiple in, multiple out. That's called an antiport, right? And again, we're relying on one molecule at least moving down a gradient and another molecule moving against a gradient for secondary active transport. The other types of active transport that we're going to talk about come under the heading, you've probably heard of these before to some extent. One is endocytosis, right? Endocytosis brings things into the cell. It expends energy, okay? So endo means inside, so endocytosis is taking this yellow substance and moving it inside the cell. There are a couple types of endocytosis I want you to be familiar with. One type of endocytosis is called phagocytosis, right? Phago refers to, here, number one, eating. Cytosis is cell process, basically. So this is when a cell engulfs solid substance and it's absorbed into eventually a vesicle. So endocytosis, cell eating. Pino, or some people say pinocytosis, is when the cell engulfs fluid by pinching off and forming a vesicle. So the only difference is in phagocytosis, it's not fluid. In pinocytosis, it is. You can also have receptor-mediated endocytosis. That's an extremely selective process where a substance binds to a receptor. Remember, it's a receptor, so it has what three properties? Specificity, competition, saturation. So that's why it's selective. It has to have the right fit. And then what happens is typically the receptor and the entire complex gets absorbed into the cell. So three types of endocytosis. Endocytosis means bringing things into the cell. Phagocytosis, cell membrane engulfs the substance, absorbs it into the cell. Pinocytosis, the cell engulfs a liquid and then pinches off and makes a vesicle by bringing it in the cell. And then receptor-mediated endocytosis, where you bring the receptor and whatever bound to the receptor, the entire complex, into the cell. The opposite, which we can see right here, we'll look at the next slide, and that's exocytosis. Exocytosis is we take a secretory vesicle, fuse it with the membrane wall, and basically spit the contents outside of the cell. All right, so exocytosis is spitting stuff out of the cell. And that creates the end of this. Again, just as a review of active transport, right? We had primary active transport, secondary active transport, and then we had endocytosis in the three subtypes, and then exocytosis. So that's completes the membrane section, S1P4.